to lecture for today. I will see if there's any other announcements that I need to make. Reminder that your homework is due when? When is our chapter 1 homework due?
Sunday at midnight.
Right. Sunday at midnight. Okay, so I just looked on mastering and not even half the class has, well, here's it, you have time. I don't expect everybody to have finished it. About half, way less than half the class has finished that assignment. So if you finish it early, great. But just make sure you're working on that. Do not save it all for Sunday afternoon. Please don't do that. Don't do that. Go ahead and get started. Here's why. You are going to have questions. In fact, I had a student email me today and said on problem 22, it's a specific heat question. I'm having trouble. Can you help me? And I said, yeah, I would love to. Okay. So we've been dialoguing about that problem. That's what I'm here for. But if you wait till Sunday, or Saturday to send me an email, I'm not good at checking my email on the weekends. So I'm available today and I'm available tomorrow. Just look through that homework, give it your best shot, and send me any questions. Hold on, I'm getting one question in the chat I need to respond to really quick. Sometimes this is hard. If you bought safety glasses and not safety goggles, yes, that's okay. Sometimes they're called goggles, sometimes they're called glasses. No big deal, as long as they're the ANSI approved. Off topic, but where do we go to find the pre-lab? Great question. Can anybody help this student out who asked that in the chat? Where do you go to find the pre-lab? Anybody been able to find the pre-lab so far?
I would say go to the lab section in Blackboard, and there's the online kind of assessments that you do after we go to lab. But above that is like a list of little, I guess, links you can go to, and those will have like your little packet with the pre-lab, post-lab, data sheet, etc. So
great, thank you, Tyler, for sharing that. So you go to the labs folder on Blackboard, and there's a list of PDFs before you click on anything else. And you find that PDF, Detecting Signs of a Chemical Change, scroll through that PDF and you'll see the pre-lab section. All great question. Do we need to bring a paper copy of the PDF to lab? You know what? I encourage it because you're going to need the procedure to do the lab. And the procedure on that PDF tells you step by step what you're going to do in lab and how to do it. Okay, so you do need the procedure, but inevitably sometimes students forget to print it out and bring it. As long as you have your cell phone or some way of looking up and having access to that PDF, that way you can complete the lab. That's okay. I had a student forget Monday and another student said, hey, do you want to take a picture of my procedure? And then she was able to do it. So we'll make it work, but I do encourage you print that off so that you can take down your data on your data sheet if you can. So all great questions. Okay. No, you will not be turning a paper copy of your lab in, okay? I'm not accepting any paper copies. That's just what the university department is encouraging us to not do, is accept paper copies. I miss the dinosaur days where we did accept paper copies of stuff, okay? I prefer that, but we're not doing that. So that's why there's the online assignment that you'll complete afterwards. So you'll take down all your data, you'll take it home with you without turning anything in, and you'll do the online assignment, and that's how you'll get your points for the lab. Another question. I'm so glad y'all are asking these questions. Since the lab is a dry lab, it's over Zoom, right? Okay, so for the dry lab people, your group B, people that are working on the dry lab this week are the group B people. Because I am in lab with the group A people, I am not able to also host a Zoom while I'm in lab with other students. So that's why if you look at the lab schedule, let me actually pull this up. I think this might help a lot of people really quick. Let me share my screen. Share screen. Share. Okay, can y'all see the syllabus? Let me scroll down. Here's our lab schedule. So look right here. This is the week we're in, right? I'm going to highlight it right there. January 25th through the 29th. If you notice right here where it says on your own, That's because the group B people will not be meeting on Zoom. You're going to be doing that on your own time. Okay. And then next week, look, the group A people, you'll be doing it on your own time because I'm not able to host a Zoom and do a lab at the same time. Okay. If I could split myself in half or duplicate myself, we could do both at the same time, but unfortunately I can't. So notice too, if you've never looked at this lab schedule, anytime it says ZBOR, what does that mean down here? You're going to have a Zoom breakout room. That's when we will meet on Zoom, okay, and do the lab on Zoom, okay? So notice we have those for a lot of weeks coming up. All of these weeks are Zoom breakouts. So we will meet on Zoom, everybody, group A and B at the same time. We'll all get on Zoom together. But for these first 2 weeks, because it's a wet lab and we can only accommodate 12 students at a time in the lab, that's why we're splitting up. Group A people come in, group B, you're on your own. So we're not meeting group B people this week. No Zoom for you. Next week, group A people, no Zoom for you. You just do it on your own because I'm meeting with the group B people, okay? I know there was a little bit of confusion on the group meet probably with some of this. So I just hope that has clarified. If there's any other questions, let me know, but I'm glad you all made it to lecture today. I was wondering how many people were going to show up after all the emails I was getting last night. So any other questions?
Yes, I have one real quick, if that's all right.
Yeah.
Do you know any websites where we can go to get some more conversion practice? Because the only issue I have is like setting up the problem and then understanding like how many meters are in a mile or how many grams are in a pound, like those kind of conversions I'm having issues with.
Okay.
If I can get
So the dry lab is intended to be practice for those things.
Oh, okay.
Okay, so the dry lab has word problems on it, specific heat practice problems on it. I don't think there's any temperature conversion, but it's got density problems. So the dry lab is intended to be practice, and you'll get points for doing that. Then the homework is intended to help you further practice those things. And what I'm going to do before exam 1, I just don't want to do it right now because you have enough work to do. But before exam 1, I'm going to go to the back of chapter 1 in the textbook. There's a few pages. I have a selected list of problems that I recommend for practice. Okay.
Yes, sweet.
As you get ready to prepare for exam 1. So go ahead and focus on the homework and the dry lab since those are due, relatively soon. Those will be practice. But if you're still wanting more practice after that, I always do this for my students. I say, here's some textbook problems that were not on your homework, not in the job, and I recommend these for extra practice. And the answers to the even numbered problems are in the back of the book, okay, for those.
All right, well, thank you.
Yeah. Okay. All right, without further ado, I think we will jump into the lecture. So we are starting chapter 2 today. And this is going to be atoms and the periodic table is what it's called. So make sure you have the right slides in front of you, atoms and the periodic table. All right. There we go. Okay, new lecture, new chapter, new hike that I get to share about. Like I said, I promise we'll eventually get to some Arkansas hikes, some hikes that we can do. Oh, sorry, I think I saw another question in the chat. I did not. For the pre-lab, do we do that on Blackboard as well? Yes, do the pre-lab on your own, like physical on the paper or on any sheet of paper. Just have your answers for the pre-lab ready, but you will put your answers for the pre-lab into the online Blackboard assignment. All right. Okay. This is obviously not a hike you can do in Arkansas, sadly. You have to drive to it a long ways, okay? So this was from our Grand Canyon trip. I took this picture at about 6 a.m. Okay, that's how bright it is. How many of you missed it being this bright at 6 a.m.? Okay, I'm very disoriented when I wake up and it is pitch black outside at 6 a.m. Another question in the chat really quick. Is the homework on mastering chemistry? Yes, it is. Okay, all your homeworks will be on mastering chemistry. But anyways, the story behind this trail, this is called the South Kaibab Trail, okay, because it's on the South Rim. So if you choose to plan a trip to the Grand Canyon, you can go to the North Rim or you can go to the South Rim. The North Rim is only open for certain months of the year though, because we went in March, so it was relatively cold. It got down in like the 30s or the 20s at night, and we camped in a tent. But we did the South Rim because there's less ice and it tends to be a little warmer on the South Rim trails than on the North Rim. Okay. So you can access these trails more months out of the year in the South Rim. So anyways, the story here is we were hiking another trail at the Grand Canyon and we ran into this couple. They were like in their 60s. We chatted with them for a little bit. They had gotten up at the crack of dawn and hiked not the entire canyon, but what I mean is they had hiked all the way to the bottom and they were on their way back out. And so me and my husband were kind of inspired and we were like, you know what? If they can do it, we can do it. Anybody ever had a moment like that? So we were like, we can do this. We're not expert hikers. Okay. We do enjoy hiking, but we're not like competitive hikers. Okay. Maybe we're a little competitive. We're not crazy. So anyways, we got up, we waited a few days to let our legs recover from the first trail we did. And we decided to hike the South Kaibab Trail all the way to the bottom. And then we hiked the other trail, the Bright Angel Trail, back up. So this is a picture of the trail, and there's a person actually on one of the switchbacks. Here's another one of the switchbacks, what the trails look like all the way down. You can't even see the bottom from here. Okay, if you zoom in, this is kind of the crevice where the river runs along the bottom, but it is a ways down. And then there's actually a little place you can camp at the bottom called Phantom Ranch, but you have to make reservations like at least a year in advance. And then we hiked back out. So let me tell you, it's not for the faint of heart. Okay, believe it or not, the tour guides and stuff, they'll tell you don't hike as much as you think you want to, because people get stuck on the trails. They just don't have the energy to make it back out, and they literally have to sleep on the trails. Okay, that happens. So don't do that. You can ride a mule down the side if you want, okay, instead of hike it, but that's way less fun. All right, let's get into the stuff for today. Lecture summary. We're going to hit Dalton's atomic theory. So what we've been doing, to kind of give you some context here, we've been studying matter at a scale that we can see it. Okay, we've been talking about how do you make measurements? How do you look at different properties of matter and observe how they change? That's all stuff we can see. But matter, there's portions of matter. There's a lot going on with matter at a much smaller scale. We're going to start looking at matter on a microscopic scale, an atomic scale. Okay, we're going to understand how matter behaves down at the level that we can't even see it. Okay, so you've probably heard of the word atom before, but we're going to understand a lot of different things about the atom today. So that's Dalton's atomic theory. And that is also structure of atoms, protons, neutrons, electrons, so on and so forth. And then lastly, we're going to get to isotopes, and we're going to look at a few things about why isotopes are important, what isotopes are. You're probably going to have a lot of questions initially when we start talking about isotopes, but hang with me. I'm going to kind of jump around on a few things about isotopes, but I think by the end, when we land, you'll have a good understanding of what I want you to know. So don't hesitate to ask me questions as we go, but I might tell you, hey, we're actually going to get to that in a slide or two. Okay, just as a heads up. All right, so to explain Dalton's atomic theory and to get your brains a little more engaged, we're going to play a quick game, and maybe you've played it before. It's sometimes people call it the close-up game or the zoom-in game. I'm showing you some pictures here, and they're really, really zoomed in and on common things that you interact with maybe daily. One of them you should interact with daily. Okay. And I want to know, what are they? Okay. Because what we're doing here, the first principle in Dalton's atomic theory is that all matter is composed of tiny particles called atoms. Okay, and to illustrate this, or to give you an analogy, we're zooming in on matter and we're looking at it at the atomic scale. So we're going to zoom in on some pictures, and I want to know, what do you think they are? Sometimes it's hard to recognize common things when you zoom in very closely. So give me your best guess. What do you think picture number 1 is? No pressure, but the first group got everything entirely right. Okay, my 8 a.m. lecture. So no pressure here. What am I seeing in the chat? Spaghetti, carpet. Okay, that's a great guess. Pasta, noodles, spaghetti, a toothbrush. I like that. Okay, I think the common answer that I'm getting here, toothbrush, Keegan says that's noodles. We're gonna write noodles. Okay, that's what everybody thinks. We'll see. Number 2, what do y'all think number 2 is? The sun, an orange, tomato, orange. Nobody thinks, so one person thinks it's the sun. Anybody think it's like the eye of an insect, just really zoomed in? Orange, tomato, fly eye. Okay. Kiki said, well, now I do. What's the most common? I think the most common answer, peach or carrot. Okay. I think the most common answer we saw was an orange. So I'm going to write down an orange. All right. What do y'all think about number 3? So it's definitely not the sun. Could be the sun, just wasn't the most common answer. Okay, we saw sponge, eraser, sponge. Everybody thinks it's a sponge. Somebody said bubble gum this morning. Anybody think it's bubble gum? We're gonna write down sponge because that's what everybody says. A pink shirt. Okay, I like this. All right, number 4. What do y'all think? Remember, one of them I said you should interact with daily. This one you should interact with daily. Chocolate, soap. You should definitely interact with soap daily. Soap, candle, soap for sure, soap, pomegranate. Okay. Everybody says soap. Couple people said chocolate. So maybe chocolate. Both of these you should interact with daily. Okay. Let's see. You want to know the answers? Boom. There they are. Okay, so for sure you got this one. This one is carrots, okay, not an orange. Number 2 was carrots. Everybody said sponge, so y'all got number 3, and 4 was a chocolate bar, so there you go. All right, so that's what we're doing with matter day. We're going to really zoom in and look at the atom close up. So let's do it. All right, that's part 1 of Dalton's atomic theory, okay? Atoms are things that are so small. Scientists for a long time actually speculated that something like the atom existed. And the way they speculated about it, they said, we think that if you took a piece of matter and you started breaking it apart, that you could do that infinitely until a certain point. So at a certain point, you're gonna come across something that's so small you just can't break it apart any further. And that's the atom, okay? And finally, with technology, we developed microscopes and things that allowed us to see that the atom existed and confirmed that speculation. Okay, number 2, atoms of a given element. This is the second part of Dalton's atomic theory. They differ from the atoms of other elements, which begs the question, how? How are they different? Well, each element is characterized by the mass of its atoms, okay? Atoms of the same element, guess what? They have the same mass, okay? Atoms of different elements, they have different masses, right? So for example, you have Na and N. Anybody know what 2 elements these are? What is Na? Sodium and nitrogen. Yes, thank you. Okay, so Na is sodium and nitrogen. And what we see some different numbers here. First off, I see a number in the top corner that is different, 11 and 7, okay? But this is not the mass number, okay? This is the number of protons, and we'll get to that later, but this is the number of protons. Now, for every element, guess what? The number of protons is also different. But what point 2 on Dalton's atomic theory says is that the masses of every element are different. And indeed they are. Sodium has a mass of 22.98977. Nitrogen has a mass of 14.0067. Now, what's the unit here? Okay, remember numbers are meaningless without units. What do you think we're talking? Is this grams? You're like, I don't know.
Moles?
That doesn't make a lot of sense. Hold on, not moles. We actually won't get to moles until chapter 6. Gram. Okay, could this even be grams? Remember, how much does 1 gram weigh? About a dollar bill. So does it make sense for an atom of sodium, which is something so small we can't even see it, to be 23 grams? No. Okay. I'm seeing in the chat, a lot of people are writing AMU. This might be something you've never heard before, and they're correct. What is a unit of an AMU? This is a unit that scientists came up with just to define how much atoms weigh. An AMU stands for atomic mass unit. Okay. Very creative, right? All right. Okay, so AMUs, that's the units that we use when we're measuring the masses of an atom, okay, atomic mass units. So this is part 2. Any questions with part 2? Just saying that atoms of different elements have different masses. That makes sense. Okay, part number 3 says compounds consist of atoms in, whoops. Somebody check, make sure you're on mute. I'm getting some feedback from somebody. Compounds consist of atoms in specific ratios. Only whole atoms can combine into compounds. Okay, what this is saying is that when you go to make a compound, water, H2O, you cannot take half a hydrogen atom and pair it up with an oxygen, or you cannot take half an oxygen atom. Atoms we don't break them apart, okay, unless you're a nuclear scientist, okay, and none of us are that. So we're gonna combine only whole atoms, all right? What that means is when you write a chemical formula, for example, if we have a formula of element X and element Y, we can never have, this is a chemical formula, we can never have a fraction here, like 3/2 or 0.5, okay? We can't do that. That is incorrect. We can only have whole numbers, okay? So you could have X2, Y3, but you couldn't have X2, Y5, 6, okay? You cannot have a portion of an atom combined in a compound. Only whole atoms combine, all right? So this brings us to our first poll question. I want you to look at A, B, C, D, and I want you to tell me, I'm going to launch the poll question, which one of these violates Dalton's atomic theory, part 3. On the slide, which one violates Dalton's atomic theory? Okay, we've got most everybody, 90% voted. You last few people, get your guesses in. 5, 4, 3, 2, 1. All right, let's look at the results. Share results. Okay. Everybody said the one that violates, most everybody, 92% of the guys. By the way, these little parentheses and percentages on the side, can y'all see those with the answers? Those just are saying how many people selected what particular answer. That's not anything to do with the answer, okay? So everybody said D violates, most people. And that's true, okay? A, we've got nice whole numbers, 2 hydrogens, 1 oxygen, all right? B, we've got whole numbers, 2 and 2, okay? C, we've got 2 hydrogens, 2 oxygen. Here, it's just the only thing that was different was the abbreviation, whether it's liquid or AQ stands for aqueous, which is also liquid, okay? So really nothing different between B and C. And then D does violate it because we've got a fraction as a subscript, and that's what part 3 of Dalton's atomic theory is saying, is you cannot have that. So, all right, good. Any questions there? Okay, let's continue part 4. This is the last part. It says that chemical reactions only change the way atoms are arranged. They do not change the type or the kind of atom you have. Okay, so when you do a chemical reaction, you can rearrange things. For example, if we have AB plus CD and we do a reaction, What this is not saying is that we're going to come up with some compound X, Y, Z. We can't do that. We can't change the atoms, okay? What we're going to get, maybe we just rearrange them. AC plus BD. All right? We got to keep the same atoms. We can't come up with totally new stuff. You can create new compounds, but those new compounds are going to be composed of the original types of atoms, if that makes sense. Questions on that? Okay, so on the exam, on a quiz, I may ask you to tell me the 4 parts of Dalton's atomic theory, or to explain a certain part, or to look at examples and tell me which one does not match or is consistent with Dalton's atomic theory. So we're gonna do some practice problems right now. I'm gonna launch another poll, I think, that has us go over these. Oh, I forgot, my favorite illustration. Nobody ever thinks this is funny, so I hope you think it's funny. Adam, what this means, question, do we have open response questions on our test? Okay, pause my discussion. Do we have open response questions on the test? Let me tell you a little story about your test. There's like 140 of you guys and there's one of me, okay? Now, if, again, we were back in the dinosaur days and we did paper exams, maybe you would have open response questions. But I do not, especially online, it's very hard for me to grade open response and get the exams back to you on time. Okay, so there's a cost benefit analysis I have to always take into account when I write exams. And it's how many multiple choice questions do I give you? How many fill in the blank? How many open response can I give you and also grade on time and get back? So the answer to that is not very many. So I'm not saying you will never have an open response where I want you to show me your work, because I think that's very, very important. If I had it my way, I would give you all open response because I want to see your work. I want to know that you know how to do it, not that you can just circle the right answer. All right, that's what I care about. Unfortunately, I don't have time to grade all of those things, or it'd be the end of the semester before I got your entire exam graded and back to you. And you have 4 exams. So the short answer there is you might have 1, you might have 2. But you will not have only open response. You'll have a lot of multiple choice, a lot of fill in the blank style stuff. Are the tests open book? Can anybody help out with that question? Are the tests open note, open book?
Yes.
Yes, they are. All right, everybody do this right here. Okay, yes. Now, face-to-face, I did not have ever open note, open book tests. I just don't want to force people to have the Respondus browser locked down, yada, 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 yada. Okay, any other questions before we move on? Going back to my funny example. What number 4 ultimately means? Who in here cares a whole lot about recycling? Okay, I actually do. Okay, we recycle at my house. My husband grits his teeth. He does it with gritted teeth. Okay. But we do. So if you care about recycling, guess what? Atoms are all recycled. That's what point 4 is saying. We just rearrange them. We reuse them in every chemical reaction, okay? Since the beginning of creation, we've had a set number of atoms, and those have just been rearranged through chemical reactions through today and into the future. So here's what that ultimately means. All of the atoms in this roadkill, all atoms in any roadkill, will eventually, maybe it will take years, maybe it will take decades, but we'll reuse them. We might even reuse them in our Subway sandwiches, okay? And in fact, if you look closely on any, I don't know about Subway, I don't know if Subway does this, but if you look closely on some sandwiches, you'll see that they'll tell you made from 100% recycled atoms, all right? How does that make you feel? You're like, I don't even want lunch anymore. I was hungry and now I'm not, okay? That's what it means. All right, let's review. Told you won't think it's funny. Poll questions. Aren't new atoms made during birth? Oh, interesting question. Okay. I've given birth to 2 children now, and I have a lot to say about this question. What do y'all think? Do y'all think new atoms are made during birth? Just open dialogue here. What do you guys think? No? No? So where do all those atoms come from? The atoms that form the baby, where do they come from? Lucy says the mom. The mom. Yeah, your babies are little leeches, okay? They just suck all your atoms. I'm not kidding. It's much more beautiful than that, guys. I love my children. But you want to know why they tell you moms are so tired during your first trimester of pregnancy? Because you are literally creating another human, okay? Your body is, yes, all of those atoms from your body are creating the human child, all right? Yeah, okay, sure. The dad does some, the mother and the father, I see that, but the mom does like 99% of it, okay? I'm not biased at all. Okay, let's look at this next question. Don't babies take your oxygen? Well, they do, but they don't take all of it. Your oxygen does feed the baby. All right, launch the poll. I love this. I love these questions. Okay, so I want to know, there's 2 questions here. Read them carefully. The first one says, which statements are consistent with Dalton's atomic theory? And here's the deal. There may actually be more than one correct answer. And I think, unfortunately, when I designed this question, I only made it to where you can select one answer. So you may want to select more than one answer if you see more than one correct, but I don't think you have the ability to do that. I'll try to be more careful when I create them in the future, but select at least one that you know is correct if there is more than one correct answer. You're going to have to put your answers into both questions before you submit, but I'll give you some time to read those. Whoops, sorry everyone. My laptop or iPad went to sleep. Okay. Okay, I'll give you about 30 to 40 more seconds. We're going to go over these. So if you're not sure, give me your best guess. It's not for a grade. And don't worry, nobody can see what you selected. All right, 92% voted. I'm going to go ahead and end the poll. Share results. So here's what people said. Remember, those percentages are just what percentage of you guys chose what answer. Okay, number 1, which statements are consistent with Dalton's atomic theory? The first one says sulfur and oxygen atoms have the same mass. Very few people pick that, and that is not consistent. Why? Because it says in part 2 that atoms of a given element are different from different elements, and we said that's because of their mass. They have different masses. All right, so the first one's not consistent. 2, all cobalt atoms are identical. That is consistent, okay? So that should have been one that was actually, most people picked that all cobalt atoms are identical. Now, some of you who already know a little bit about isotopes may be thinking, that might not actually be quite true, okay? And we'll get to isotopes. But they are all identical in the number of protons they have, and their masses are all almost identical when you talk about isotopes. But we haven't got there yet, so according to you right now, they're all identical. So that is consistent. Okay, potassium and chlorine atoms combined in a 1-to-1 ratio to form potassium chloride. What does this mean? I actually want to write this one out. Okay, potassium, if you look at the periodic table, is K. Chlorine is Cl. You don't have to know this, but what it's saying is that if you take one atom of potassium and one atom of chlorine and they come together, you make KCl. And remember, when you just have one atom, you don't write the subscripts in. You don't write K1, Cl1. You don't need to because you just wrote the letters. But are these whole numbers? Yes, those are whole numbers. So those are whole atoms. That is consistent with point number 3, okay? So 3 is also, those middle choices are both correct. Last one, lead atoms can be converted into gold. I wish, we all wish, we'd all be rich if that could happen. Nope, we cannot convert atoms of one element into another element. All right, so just the middle two are consistent there. On question number 2, which statements are not consistent? The first one, all carbon atoms are identical. Well, that is consistent, so that's not what we're looking for. Next, an oxygen atom combines with 1.5, not consistent. You cannot break apart half a hydrogen atom to form a water molecule. So that one is not consistent, and that's what most everybody picked. Next one, 2 oxygen atoms combine with carbon, 1 carbon, to form a molecule of carbon dioxide. Let's look at that. Okay, what that is saying is 1 carbon atom and 2 oxygen atoms. Okay, if we had 2 of those, are going to combine and we're going to get CO2. So you need to ask yourself, in this chemical formula, are all my subscripts whole numbers? And they are 1 and 2. So that's consistent, but we're not looking for the ones that are consistent. We want the ones that are not consistent. So far, that's only the second choice. Lastly, the formation of a compound involves the destruction of what? No, we cannot destroy atoms, okay? I don't have the power to do that, at least. So that is the poll questions. Any lingering questions on this stuff before we move on to atomic structure? Keegan, so if you are born or made up of all the atoms you'll ever have, do they just spread out as you grow? Atoms confuse me. Well, if you never ate anything or drank anything or breathed anything, then yes, but you would die if that happened, okay? So here's the way it works. You are constantly feeding your body chemicals or form elements, okay? Carbon, nitrogen, oxygen, different vitamins, different, obviously proteins, fats, carbohydrates in the food we eat. And we're breathing oxygen. And guess what? Your body literally grows from those things, okay? It extracts the carbon that it needs, it extracts the oxygen that it needs, and it uses those to create ATP and new cells. And that's how you grow, okay? So no, it doesn't just formulate new atoms. You feed it the atoms that it needs to grow, okay? All right, moving on. Great question, though. Structure of atoms. So we're going to talk about protons, neutrons, electrons. Here we go. What does an atom look like? Well, they're very, very small. How small are they? The way we measure an atom is its diameter. Okay, so there's 2 parts to the atom. The first part we call the electron cloud. And that is where the electrons are. They are floating around, zooming around. Electrons are constantly moving, okay, in the electron cloud. And that is this part in blue, this kind of large blue sphere. I'm outlining it. Okay, so the diameter of the atom is measured from the electron cloud with these black lines. And look how small it is, approximately 10 to the minus 10 meters. Okay, do you guys remember a nanometer? How many nanometers are in 1 meter? Anybody remember? A million? No, more than a million. A billion, yep, so 10 to the 9. So what this is saying, 10 to the minus 10 meters is even smaller than 1 nanometer. Okay, that's how small atoms are. We can't even see them with the naked eye. So electrons are in the electron cloud and they're moving. They're constantly moving. You know what's funny? When we had a baby shower for our first daughter, someone literally got me a book that said Quantum Physics for Babies. It was a book and it was all about electrons moving in the electron cloud. And I've read it to my daughter. So it's always funny when I do that. But this is what part of the atom looks like. Now, if we zoom in on this little sphere, this is called the nucleus. And in the nucleus, we have the other subatomic particles. So we've talked about electrons, which, by the way, if you notice, let me go back to electrons for just a second. I put this little minus sign on electrons, and I'll explain this further in just a second. But when we write out electrons, we always put a little minus sign with them. Okay, don't just write E for electron. It's an E with a minus sign, and we'll come back to that in a second. Okay. Now, with the nucleus, we have the other subatomic particles, protons and neutrons, and they are packed tightly together and they are not moving. They're stationary, okay? They're sitting there in the middle. Protons have a positive charge, so you could indicate that with a plus. That's all these little red spheres. Neutrons have no charge, okay? And so that matters, because think about this. How do all these protons stay nicely packed together if they're all positively charged? Anybody played with magnets before? And when you put magnets together, sometimes they zoom together if they're attracted. But if you put similar ends together, what happens? There's repulsion, right? They push apart. So think about this. We're pushing together a bunch of things with positive charge. Why are they not just repulsing each other? That's the beauty of neutrons. Neutrons are packed in there to help hold all of those protons together, or else they would just push each other apart, okay? Because opposites attract, like charges repel, remember? Look at the nucleus. Look how small it is, 10 to the minus 15 meters. So way, way, way smaller, 1,000,000 times smaller than a nanometer. All right, this is incredibly small stuff here. So those are just the 3 subatomic particles and a little bit of how they're arranged. Protons and neutrons in the middle. Electrons are flying about around, and they make up the size of the atom. And protons and neutrons will help us identify the atom, and they make up the mass of the atom, which brings us down to this table. Let's fill in these blanks. So we got protons, neutrons, electrons. What are the symbols for these things? Proton, we abbreviate with a P. Neutron, an N. Electron, we do the E with the minus sign. Okay, what about the mass? All right, well, in grams, these numbers are going to be ridiculous because, again, think about how much does a gram weigh? 1 gram is about the mass of a dollar bill, okay? But we are talking about things that are so small we cannot even see them. Sometimes it's hard to even see them with microscopes. So look at their mass in grams. A proton, 1.673 times 10 to the minus 24. That's insane. Neutron, 1.6 or 675 times 10 to the minus 24. So what do you notice about neutrons and protons? Their mass is really, really close, about the same. And electrons, 9.11 times 10 to the minus 28. My mind cannot even comprehend how small that is. But what I notice is that the difference of these two versus an electron, electrons are over 1,000 times smaller in mass than protons and neutrons. Okay, that's important. That's important because when you go to the next column, instead of using these ridiculous exponents, let's just communicate the mass in AMUs. It's going to be much easier. And in AMUs, scientists say proton weighs 1. It's a lot easier, right? Thank goodness. What about a neutron? Well, if in grams their mass is about the same, guess what? In AMUs, their mass is the same. 1 AMU for neutron too. But because an electron is technically 1,000 times smaller when it comes to its mass in grams, we just say it doesn't weigh anything compared to protons and neutrons. Okay. What about the charge of these things? Protons, we said up here, are positively charged. So that gets a plus sign. You can write +1 if you want, or just writing plus indicates that it is a +1 charge. That's how much charge it has, +1. And neutron, nothing. Electron, minus or -1. Okay, this is all important stuff to know. I want you to be able to tell me these things. If I gave you a table like this and said, fill it in, I would want you to be able to do that. But even more importantly, I want you to know why these things are in an atom and what they do. They all have a role to play. They're all important. And why are they important? Well, the electron makes up the size of the atom, right? Because it's the electron cloud that really tells us how big the overall atom is. And they are responsible for the chemistry. What do I mean by that? Another word for chemistry here is they're responsible for the behavior. All right. Now here's the deal. I don't mean some atoms have good behavior and some atoms have bad behavior. I just mean some atoms are really reactive and some atoms are not very reactive at all. We call those atoms inert. They don't really react with much, those elements. But some atoms are very, very reactive. For example, look at this picture down here. You probably recognize, or at least could take a guess if you look at the letters and numbers on what this is. Okay, this is a hydrogen bomb. And guess what? Electrons are responsible for that amount of energy in a hydrogen bomb. Okay, isn't that astounding? Things we cannot see create an explosion so massive that it can do an insane amount of damage. All because of electrons. So they're responsible for how atoms energy that's released and the aftermath thereof in chemical reactions. Okay, what about protons? What's their role to play? You see their charge, you see their mass in AMUs, and yes, there are some decimals here. I don't want you to confuse that with what we wrote up here. It's essentially 1. All right, you can just tell, you can report these numbers if you're asked for what the mass is. I'm not going to make you memorize all those decimals. Protons, they identify an atom. Okay, if you have a certain atom and you want to know what it is, if you can determine how many protons are in that atom, you can tell me what element it is. Okay, because we identify elements according to how many protons they have. They also contribute to the mass of an atom. All right, contribute to the mass. And what about neutrons? Neutrons contribute to the mass. Okay, because they weigh something. Electrons don't weigh anything, so they do not contribute to the mass of the atom. But neutrons weigh something, protons weigh something. Neutrons are also, they come into play. Their role is more so with isotopes. Okay, so what I mean there is that neutrons are how we get isotopes, all right? Different numbers of neutrons in an atom. And we will explain that further. So I know you probably have some questions right now, but just hang on to those. We'll get to that in a minute. Okay, any other questions with this? So if I ask you the role of each of these things or gave you examples and had you identify, I would want you to be able to tell me. In fact, I think I have a poll question on this. By the way, if you want another explanation, plug this link in. It's an old TV show, and it's got a really fun clip that's 2 or 3 minutes long about the structure of atoms, okay? It's a fun analogy. I used to show this, but we're not going to take that time to watch it today, but I think you'll enjoy it if you go check it out. Okay, let me launch this poll. This is on atomic structure review. So I think you can check more than one box this time. So check all that apply. Which statement about subatomic particles are true? Please remember, I'm asking you all to have your video on for lectures. If you have a special circumstance you need to email me and let me know about, that's perfectly fine. But so far, nobody has done that, so. Okay, 75% voted, 80%. All right, I'm going to give you about 10 more seconds. All right, I'm going to end the poll. Share results. Okay, if you didn't get your answers in, it's okay. We're going to go over these. Again, none of this is for a grade. Which statements about subatomic particles are true? So here were the results. Most people pick the top 3 choices. So the first one says if an atom has an equal number of protons and electrons, it will be charge neutral. That is true. Why? Because protons and electrons both carry a magnitude of 1 when it comes to their charge. So for example, if you have some atom and it's got atom X and it has 10 protons, 10 electrons, when it comes to the charge, how many positive charges is that? Well, each proton carries a +1. So that is 10 times +1. That's +10. Electrons, that would be 10 times minus 1. So that's minus 10, and that adds up to 0 charge neutral. Okay. So all atoms, by the way, all elements in their natural state, before they start reacting with things and bump into other atoms, they're all charge neutral. They all have the same number of protons and electrons. They're all charge neutral in their natural state. When you get to chapter 3, we'll see how some of these rules can be broken. But for now, in their natural state, things are charge neutral. So yes, the first one is correct. Electrons are attracted to protons. That's the second one. And that is true, okay? Opposite charges attract. Negative is attracted to positive. So that's also true. And then the next one, electrons are much lighter than neutrons. Yes, that's true. We said over an order of 1,000. Okay, if you want to prove that again to yourself, just look at their mass in grams and see how different they are. Lastly, protons have twice the mass of neutrons. No, they both are very, very similar. Okay, we say they're essentially the same. So protons weigh the same as neutrons. They do not weigh more. So those first 3 choices were correct. The last one was not. All right, moving on. Any questions so far on Dalton's atomic theory or subatomic particles? Okay. So that brings us to the last thing for today, isotopes. So I'm going to introduce why isotopes are important. And then we're going to pause and we're going to look at what does A and Z mean. Okay, these are different properties that help us understand isotopes. Then we're going to talk about natural abundance. Okay, different isotopes are present on the planet in different amounts. And we're going to look at how to calculate an average atomic mass for isotopes. So let's go. Why should you care about isotopes? Anybody have an answer to this without looking at your slides before we get into it? Anybody take like a history class or a science class in middle school and you learned about like dating fossils? How do they come up with the dates of different fossils? Carbon dating, okay? So that's one thing that isotopes are used for, okay? We take an isotope of carbon and it's unstable, and anyways, I'm not gonna get into it, but that's one reason isotopes are important, but here's another reason, energy, okay? We extract energy from isotopes, or we can generate energy using isotopes. So nuclear fusion, I know that's a fancy word, of hydrogen isotopes produces large quantities of energy. Okay. So first off, what is nuclear fusion? Is anybody ever driven by a nuclear reactor on like the interstate? It's usually the big towers that have like the big smokestacks. I think there's one in Russellville. I know there's one in Russellville. And what they do is they do nuclear reactions there. And but nuclear fusion is where you're forcing atoms together. Okay. Sometimes atoms don't want to go together, but if we use enough energy, we can force them together. That's nuclear fusion. We fuse them. And when you do that with isotopes, especially isotopes that are not necessarily stable, you can create reactions that produce large amounts of energy. So for example, I have 2 hydrogen isotopes here. The orange spheres are protons. The gray spheres are neutrons. So you have 1 proton here, 1 neutron. So that's where we get H2. That 2 is just the sum of protons and neutrons in the atom. We'll talk more about this in a minute. So that's an isotope of hydrogen. Why? Because hydrogen, natural hydrogen in the universe looks like this. 1 proton, so this is just 1 proton in the whole atom, in the nucleus. No neutrons. That's natural hydrogen. So when you start throwing neutrons into the nucleus, now we have hydrogen isotopes. And look at this one. We've got a proton and 2 neutrons. So that's an even bigger isotope, okay? And when you fuse these isotopes together, you produce tons and tons of energy. What is a capital MeV? Well, EV stands for electron volt. Don't worry about it. It's not a unit you're going to know here. But M stands for mega. This is not a prefix that I introduced to you, but when you put mega in front of a unit, guess what it does to that unit? It makes it really, really big. Okay, it makes it mega. So this is just to show you, we get tons and tons of energy when you fuse isotopes together, okay? Don't worry, I'm not going to ask you about a reaction like this. I'm not going to ask you to tell me the products. I just wanted to use it as an example for why isotopes are important. Okay, another reason isotopes are important, this one will click with a lot of you guys more. Medicine, okay, we use them in medicine. Some isotopes are unstable. And when you have unstable isotopes, decomposition of these unstable isotopes releases, you guys have heard this term, radioactive energy. Okay, radiation. You know somebody maybe that's gone through radiation therapy before. And that is used to kill cancer cells. Hold on, let me respond to one thing in the chat really quick. Okay, so how does this work? Using radioactive liquid therapy to treat thyroid cancer. So I'm just going to give you an example with thyroid cancer. Thyroid cancer is very common, unfortunately. What we do is we use iodine, okay? Iodine therapy. We use an isotope of iodine. It is iodine 131. That is so when we talk about isotopes, we communicate them by their mass number. So iodine 131. And this specifically targets the thyroid and hopefully has very little effects on other parts of the body. So we're going to walk through these steps 1, 2, 3, 4 to show you an illustration of how the isotopes are used to kill cancer cells in the thyroid. So first off, patients will ingest radioactive iodine. They drink it or they take a pill. Then the iodine molecules are absorbed through your digestive tract because you're drinking it, and they get into your bloodstream, and they all go to your thyroid, okay? Or you hope that 99.999% of them go to your thyroid. Now, your thyroid does absorb all your iodine, okay? And in fact, if you are deficient in iodine through your diet or whatever else, you might run into thyroid issues down the road. So make sure in your diet you're taking in enough iodine. You can look up different foods and sources of iodine. But anyways, it all goes to your thyroid, and the thyroid, as we just said, needs iodine to work. So it absorbs all of that, and then the radiation from the isotopes, the isotopes of iodine, they destroy cancer cells. The only unfortunate thing here is they also destroy normal cells, right? There's always a kind of a cost benefit analysis you have to think about when you're doing radiation therapy, because you're going to kill off a lot of healthy normal cells. And that's why a lot of cancer patients lose their hair. They become very sick sometimes because you're killing a lot of normal healthy cells in the process. And that's the price you pay when you choose to do radiation therapy. But hopefully it does get rid of the cancer for you. So it's also very, very important, because guess what? Radiation, sometimes it has very few boundaries. So radiation can also emit out of your body, all right? And you want to be careful if you're a patient receiving radiation therapy that you're not exposing other people unintentionally to harmful radiation just by being around them. So that's why it's always important that proper safety measures are taken for patients who receive this kind of treatment. Any questions on this and why isotopes are important? And there's many more reasons than this, by the way, okay? These are just 2 examples. Okay, so I'm going to pause on why isotopes are important, and let's talk about 2 things, Z and A. All right, Z is what we call the atomic number. For any element we can identify, Z is just the number of protons in an atom, okay? So if we're looking to identify that, we got to go to the nucleus, right? The nucleus is where the protons are. If you're looking at a periodic table, for example, I have carbon, the atomic number is always communicated above the elemental symbol. It might be directly above it, or it might be in the corners, okay? Different periodic tables put them different places, but it'll be above the atomic symbol. That's where you find the atomic number. And the abbreviation for that is Z. Don't ask me why it's Z and not A. This is the identity. I'm just going to put ID. It's the identity of an atom, okay? So if you know, guess what? Carbon. If you run across a proton or an atom and it has 6 protons, you know it's always carbon. If you run across an atom and it has one proton, it's always hydrogen because that identifies the atom. All right, carbon always has 6 protons. Let's move on to the next thing. Any questions on Z? Sorry if that felt fast. Z, atomic number, okay? Number of protons. All right, mass number. This is where chemistry gets incredibly comical for me. Guess how we abbreviate mass number? With an A, okay? You're going to get this confused. I promise somebody's going to get it confused. You're going to think A is atomic number. Rightly so, but A is mass number. So this is mass number. This is the sum of protons and neutrons. In an atom, okay? Remember, we said protons require the neutrons. They're there on purpose to buffer the positive charge to keep those protons from flying apart. Those neutrons buffer the charge repulsion and keep those protons packed in the nucleus. All right, now, knowing this, let's look at an example with a particular element of just these properties. Copper, we abbreviate copper Cu. It has been found that copper can be stable with 34 neutrons packed in the nucleus or 36 neutrons packed in the nucleus. What? This is interesting. So if we have this, let's actually calculate what is Z. Remember, that's the atomic number. And what is A? That is the mass number for each of these two forms of copper. Well, there should be no calculation for Z. Z, we just go to a periodic table and we find Z on the periodic table for copper. Anybody have a periodic table to look at? Okay, I put one on here and I'm very disappointed because when you zoom in, look how good the resolution is. Isn't that fabulous? Can anybody read that? 29, okay? So that's Z for both of these because they're both copper. So Z is the same. So Z for, I'm going to abbreviate, Cu is going to be 29. And that means 29 protons. Okay, so anytime you're asked what is Z, you just go to the periodic table, you find it right off there. But what is A? So for copper, we're going to call it copper 34. What is A? A is equal to the sum of protons and neutrons, okay? So guess what? If we have 34 neutrons, we've got to add that to 29 protons. So 34 plus 29. For copper 36, with the 36 neutrons, A equals 36 plus 29. Okay, so what do we get for the first one? What's 34 and 29?
$63.
Yes, 63, and then plus 2 more would be 65 for that one. Okay. Any questions on how we just calculated A, the mass number, or determined Z, the atomic number? Okay. Now, let's actually define what is an isotope. So we're going to continue with our illustration on copper. So now that we added up the 63 and the 65, this is how we identify isotopes. We identify them according to their mass number because it's their mass numbers that differentiate them. It's the mass numbers that are different because different numbers of neutrons. So we say copper 63 and copper 65, we would call these copper isotopes, okay? Both are copper because they have 29 protons. And remember, it's the number of protons that identifies the atom. But they're isotopes because they differ from each other in the number of neutrons. Okay, so an isotope is an atom or atoms of the same element with varying number of neutrons. It's an atom of the same element with varying number of neutrons, okay? And we can calculate these things. We can determine how many neutrons something has, how many protons something has with A and Z, which is just atomic mass is the number of protons. No, sorry, mass is protons and neutrons. Okay, so just P plus N. Atomic number Z is just the number of protons. Okay, that's the review. All right, lastly, before we get into percent abundance and calculating average atomic weight, just to show you, remember when I showed you nuclear fusion earlier in that image, we had the H2 fusing with the H3, okay? You might have been confused as to why the 2 and the 3 were written the way they are, but that's because we have a shorthand notation we use for showing or writing isotopes. You can write the symbol of the element, and then on the left-hand side, you can write the mass number on top and the atomic number on bottom, okay? So for example, iodine 131. Let's look at iodine 131 really quick. We would write it like this because that's the mass number for that isotope of iodine. We were talking about how it treats thyroid cancer. Now, if we know the atomic number for iodine, let's go to that periodic table I had. I don't even know if I can read it off of here. I had trouble this morning. 49, 50, 51, 52. I think that's 53. Somebody correct me if I'm wrong, but from my best guess, it was a 53. So that's what we would write for iodine, 131, okay? Now, if I asked you how many neutrons are in iodine 131, could you tell me? I said, how many neutrons? In fact, I want you to figure that out right now. How many neutrons are in iodine 131? How do you get that? Kendall said 78. 78. Okay, how do we get that? Subtract the number of protons, yes, from the mass, okay? So because this is the mass number 131, you'll do 131 minus 53, okay? Because this right here, remember, is neutrons plus protons. So we just subtract off the number of protons, and that gives us the number of neutrons, okay? All right, we're going to skip over this. 1, there's a typo. 2, for time's sake. Okay, do the same thing for carbon. Carbon 14, give the total number of neutrons found in this molecule. Okay, Allie says 8. How do we do this? You take the mass number, which is on top, which is 14, subtract off the atomic number, which is 6. This gives you the number of neutrons. All right, good. Okay, let's quickly, because we don't have a lot of time left, talk about percent natural abundance, and then we're going to look at how you calculate atomic mass for elements. Percent natural abundance, what does this mean? So you can guess by now, certain elements have many, many, many isotopes. Okay, copper, we looked at, it has 2 isotopes. Some elements have no isotopes. For example, sodium. 100% of all sodium on the planet is just sodium 23. Okay, there's its mass, really close to 23, so we round to the nearest whole number. 100%, no isotopes. Guess what? Nitrogen, it weighs 14. Okay, nitrogen 14 weighs, well, actually, this is the communicated atomic mass for nitrogen. But some nitrogen, 99.64% is what is the isotope nitrogen 14, and 0.36% is nitrogen 15. Okay, and you could calculate the number of neutrons in each of those. So let me ask you this: which of the following in 2 molecules? So nitrogen naturally exists as 2 atoms put together in a molecule. Some elements exist that way. And we have nitrogen in our atmosphere. You're breathing it right now. So in the room that you're in, what kind of nitrogen molecule are you breathing in? Is it 2 atoms of nitrogen 14? Is it an atom of nitrogen 14 bonded with an atom of nitrogen 15? Or 2 atoms based on the percent natural abundance? Which one do you think, A, B, or C? All right, I'm looking at the chat. Everybody says A. And that would be correct because pretty much all nitrogen, the natural abundance, its natural is nitrogen 14, okay, that isotope. Nitrogen 15 isotope's not very abundant. But when we calculate the mass of any element, we have to take into account how prevalent each isotope is, what its natural abundance is. So when we calculate the atomic weight, and these are the weights that are communicated on any and every periodic table, it is a weighted average of the atomic mass of all the isotopes of that element. Okay, so to calculate, if we're going to give one mass for an element, even though there's multiple isotopes sometimes, we have to calculate an average of all the isotopes, and we report that number. So that's what we're about to do. With copper, we're going to just keep with our example with copper. So the type and the natural occurrence of an element's isotopes determines, that's how we calculate the atomic weight. So let me show you how we do that, and then we're going to be done. So remember, we had copper 63 and copper 65. Okay, we determined that earlier. And in AMUs, here's their exact weights. You can see they're not exactly 63 and 65, they're pretty close. So we're going to take the exact weights for those individual isotopes, and we're going to multiply them by their percent natural abundance. But we're going to first convert those percentages to a decimal. How do you convert a percent to a decimal? Anybody know? So if we're going to do it for the first one, you divide by 100. Okay, so let's divide this by 100. You get 0.692. And then you divide by 100 and you get 0.308. Okay, now we have their percents as a decimal. So we're going to just, for every isotope we have, here we only have 2 isotopes. You could have more than 2, but in this example, we only have 2. We're going to start with copper 63, take the mass, which is 62.9396 AMU. And we're going to multiply that by the percent as a decimal, so 0.692. So this one was for copper 63. Now we're going to add to that, we're just going to add up all the isotopes. We'll do the weight or the mass in AMUs for copper 65. And we're going to multiply that. I got to zoom in because I'm at the edge. We're going to multiply that by 0.308. That's the percent as a decimal, and this is for copper 65. Okay, so because there were only 2 isotopes, after we do it for both, we're done. If you had an element with 3 or 4 or 5 isotopes, this would be a much longer math problem. But when you do that, you should find that the average, the atomic weight for copper reported on the periodic table is 63.55, okay? Somewhere in the middle, a little above 63. Okay, I know that was probably fast. So if I rush through that, if you're like, I don't even know what just happened, I will post the lecture recording tonight and you can rewatch any of this. We have about 2 minutes left. I will field any questions on anything you think I blazed through. But we did get where I wanted for today. I do want to launch one little